Hey everybody, last time we talked about how to find the area of a half circle, rectangles, triangles, parallelograms. Sometimes we combine shapes and we had a rectangle with a half circle on the end, or maybe a triangle with a parallelogram attached to it. Kind of like that. Okay, we talked about a couple different shapes. Well, what if it wasn't a shape that there was necessarily a formula for? I mean, for these down here, we all have formulas. Even adding different formulas together, we're smart enough that we're able to create a formula. We're able to find out the area of those shapes. What if it's not like that, though? What if it's a shape like this? It's not a half circle. It kind of looks like a half circle, but it's not. It's not a half circle. It's a parabola. Okay, it's definitely not a half circle. So how do we find the area right here? Well, today we're going to talk about how to approximate it. All right. So when I'm talking about approximating, here's what I mean. Okay. If I drew a couple of rectangles in here, because we know how to find the area of a rectangle. What if I drew a rectangle like this, maybe another one like this, another one like this, then another rectangle that would just be at 0, okay? That somewhat follows the same pattern. So we're getting kind of close. Over here you can see it's overestimating. So if we took that area, stuck it here, this area, stuck it there, we're getting kind of close, right? We're getting kind of close. Or I could go from the other side. I could do what's called a left approximation. I could go from the left side, so I'd have 0, I'd have a rectangle right there, I'd have a rectangle starting here, I'd have a rectangle starting there, okay? Again, I could figure out the areas of those rectangles, add them together, and it would be kind of close. Is it going to be the exact answer? No, but it will be pretty close. So, let me erase some of these black lines. What if we made even more rectangles? What if we just maybe double it? Maybe had a rectangle right there, and right there. So we come over there, down like that. Are we starting to get even closer to what the actual value is? Absolutely. Let's see, right there's the dot. Okay. This is using left approximations. Actually, that's like left and right. Where did I go off? Left. Left. Oh, that's right off, right there. You got a left approximation, a left approximation, a left approximation. Okay. So you see, this is starting to get closer and closer and closer. If we did even more rectangles, let's erase this a little bit. What would it look like if I did even more rectangles in this problem? How much closer would we get? We've got one, there's a halfway point, there's a halfway point, there's a halfway, there's a halfway, there's a halfway, there's a halfway. As you see, as we start putting in more of these approximation points, the value is getting closer and closer and closer to being the truth. Okay? As we start doing more and more and more of these little rectangles, we're getting closer and closer and closer to the actual value until you get to infinity. Now, can we really draw an infinite number of rectangles? No, we can't. We definitely can't. There you go. And so you see we're getting even closer. You take each of these little chunks over here, start plugging them over. We're getting so close to what the actual value is underneath this curve. So, when we're doing this, usually we just go based off a certain number of intervals. So from 0 to 4, we might have 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So we don't go through and do a million of these tiny intervals inside, all right? So here we go. When we are doing these, let's do one where we're trying to use left approximations. Okay, there's left approximations, I guess left approximations, and there are right approximations. With the left approximation, what I always start off doing is I draw a line down from each of these dots. So I've got it separated into the different columns. Okay. Now if I'm using left approximations, I'm going to draw a rectangle based off the leftmost point. So here the leftmost point is right there. So if I draw a rectangle, well, that's more just like a straight line going across it. That's not really even a rectangle, it's just a line. Let's look at the next box. Okay, some of these are going to over approximate, some will under approximate. It averages out. Here, you can come up, the leftmost point is right here. That's my rectangle. Has a height of 3. It has a height of 3 and a width of 1. What's the area? 3. Next one, leftmost point, right there, has a height of 4, so I'm writing that off to the side, has a height of 4, a width of 1. So what's the area? 4. This last section, width of 1, height of 3, 3 times 1 has an area of 3. So roughly, what is the area under this parabola? Well, it's 3 plus 4 plus 3. So the area is roughly 10. Okay, that's using what we call left approximations. Let's try it again using right approximations. Okay, so that's using left. Now let's try it using right. All right, this time let's do this using right approximations. So with right approximations, what we do is we look at the same interval, but we go with the rightmost point instead of the leftmost point. That's the only difference. So here, the rightmost point is right here. Okay, has a width of 1, a height of 3, so what's the area? 3. Here you go, the rightmost point is up here, has a width of 1, height of 4, so what's the area? 4. Draw a rectangle, because that's the rightmost point. Height of 3, width of 1, so it has an area of 3 here. The rightmost point, oh, 0. What's 0 times 1? 0. 3 plus 4 plus 3 plus 0. Right has an area of 10. It's also estimating about the same. Now there's some crazy ones that you can do where you're more of drawing triangles on each of these. We'll get into those later, not right now necessarily. But that's what we're doing right here. We're summing, kind of like how we talked about summation notation. Remember, we were adding different pieces together? That's basically what's happening here. We're just adding different pieces together, okay? All right, so here's another problem. We've got this graph here, okay? We need to find the area under the curve using left approximations and right approximations, just to compare the differences, all right? So let's start off doing the left approximations. So I'm gonna go through, I'm gonna mark, okay, I'm gonna mark all the areas. So if we're using a left approximation, well, left would be here, so we've got, well, that line. The next one would be here. That's 2 high, 1 tall, so that gives me an area of 2, plus here, well, actually it's negative 2 because it's below the x-axis. Plus, let's see here, if we're using left approximations, that's 0. On this curve, what's the leftmost point? That one, which is a 1, okay, 1 by 1. So we've got 0 plus negative 2 plus 0 plus 1, which gives me a total answer of negative 1 for my left approximation. Does that seem right? If this is negative, this is positive, does it equal out to be negative 1? I don't know. Remember, this is just approximating. This is not telling us exactly what the answer is, okay? So let's try it now with right approximations. Let's see if we get a different answer. So with the right approximation, I'm going to go off the rightmost piece of this curve. The rightmost point is right here. It has a height of negative 2, width of 1, so we've got negative 2. The rightmost point on this curve, this section of the curve, is right there, so that's 0. The rightmost point on this curve is 1. Got 1 by 1. So 1 times 1 is 1. And the rightmost point on this curve is 4. times 1, which is 4. That gives us a total value of 5 and -2, which would be positive 3. So you can see your left and right approximations, they can vary quite a bit. They really can. My guess is that it's somewhere between those two approximations. My guess is it's somewhere probably a little more than 0, but maybe a little less than 1. All right. And if we used other methods, maybe we drew little triangles in each of these instead, we'd get a little bit closer. That's not what we're doing today, but that is an option if you're trying to get more and more and more precise. All right. We'll try one more. Alrighty guys, I want you to try this one on your own. Pause the video if you need to. Try the problem using left approximations and right approximations. Try to think which one's going to be more accurate in this case. Which one's more accurate? Give it a try. Alright, you should have your answer by now. If you don't, pause the video, give it a try. Here we go. Let's try with left approximations first. So we have this little curve right here between 0 and 1. Looks like the leftmost point is at -2, so it has a value of -2. -2 times 1 is -2. All right, next up, we've got this piece here. What is the leftmost value? It's 0. Next up, we've got this one. That's 2 tall, 1 wide, so that's 2. And finally, we've got this one here, left, which is 1. That gives us a total left approximation of about 1, okay? Next up, let's try it with right approximations. Let's see what we get when we do right approximations. There you go. When we're doing right approximations, well, on this curve, the rightmost point is 0. So we're not even taking into account any negative numbers, okay? And then here, the rightmost point is 2. 2 and 1, well, 2 by 1, I should say. This is the value of 2, so we've got 0 plus 2 plus the rightmost point on this curve is 1 plus 0 gives us a total value of 3. Which one is more correct, the left or the right approximation? Personally, I feel like if you've got this part here and this part, these are about the same, so they'd probably cancel each other out. So it's really just this piece that we're looking at. There's obviously 1. If you take this piece, flip it up, stick it on there, I'm thinking that's going to be a little bit more than 1. If you combine this little square and that little piece, I think that'd be a little bit more than 1. So 1 plus something a little bit more than 1. I'm guessing it's going to be a little bit more than 2. So in this case, I think the right approximation was actually a little bit closer than the left approximation. But if you notice, the right approximation didn't even take into account the negative. I could be off. I don't know. All right, that's just my approximation. All right, there are a couple problems on the next page. They are a PDF. I think there's 8 problems that I want you to try. Some of them already have the graph drawn. Others, you need to draw the graph. You might want to use the Desmos graphing calculator to do that, okay? The time is yours. Holler at me if you have any questions.